Okay, last day we started the concept of linear transformations. We want to continue on, so let me do a quick summary of what it is that we have in the most generic form. I've got two vector spaces, V and W, and they could literally be anything. I could have a polynomial space, and over here have a space of matrices of a particular size. It doesn't matter. There's two vector spaces. We are going to have a map, if you will, called T. In baby algebra, when you first learned functions, you hopefully learned something called a mapping. That's where you took elements of your domain and showed where they transferred into the range. And I don't remember, or know if you remember doing this. Something as simple as this. And I said, now, what is your domain in baby algebra? And what is your range? In this case, it would be 2, 5, 6. A mapping literally was something this simple. And then I'd say, is this a function? And you would say yes, but why? That's really the important thing. Why is this a function? And then I got to know, what's the definition of a function? Because every element here has a unique output over here. What if? I'm adding an element now. Is this still a function?
Yes.
You're sure? Yes. Be bold in that. Yes, it is still a function. But what is it not?
One-to-one.
It's not one-to-one anymore, because the output of 6 came from different inputs. It is still a function, it is not one-to-one. And that's where we sometimes have issues of confusing them because their definitions are so similar. Function means every input has a unique output. One-to-one means every output came from a unique input. But we only use one-to-one if it's already a function. You don't take things that are not functions and describe them as one-to-one. That doesn't have any meaning really. So a linear transformation is a lot like a function. But my linear transformation could look something like this. Yeah.
So if the other point you'd added was 4, 7, it would be a function then? Because it would
Yeah, in fact, let's do exactly that. When I teach remedial algebra, I would show them the exact same stuff so they get a mental picture, and you always use just a few things so it's easy. So we're talking about a mapping. So now Chase's suggestion is, what if I make that point instead 4, 7? Now it fails to be a function because the input to the output is not unique. So forget one-to-one, that's not even on the table anymore. A linear transformation is not automatically one-to-one, but it is a function. But if I'm going from a higher dimension to a smaller dimension, then right off the bat, I must send an infinite number of things to the additive identity. We looked at a problem like that last day. In every linear transformation, there is a matrix that can describe the transformation, even if your original isn't, okay? Even if the original thing is not that. I can have polynomials go to polynomials. But I can create a matrix situation that will still answer the question. I don't want it to get complicated, so for right now, we're probably going to stick with pure vectors to pure vectors because it makes the notation easier, makes the explanations easier. But I'll still use the term additive identity rather than zero vector because additive identity applies to all vector spaces. Zero vector only applies to vectors, okay? So if we now said, let's assume this is Rn and this is Rm, N and M do not have to be equal. So let's kind of go over what we did last day. If I'm going from bigger to smaller, then there is actually going to be a kernel of T that is not just the zero vector. I'm going from bigger to smaller, R3 to R2. I'll even write it like this. Everything in here gets mapped to the one thing. Bigger to smaller, that's an absolute guarantee. And if you're saying, well, why is that true? Because the matrix associated with it. What is the shape of the matrix? if I had the matrix of a transformation, if I took A times V and got W, where V is a vector here, T of V equals W is a vector here. I can perform this with a matrix multiplication. Tell me the dimensions of A. We did this last day. Do you remember? You guys remember what is the dimension of A? Well, my input has to be in Rn, so I'm doing a matrix multiplication to make it easy on you. And what am I getting? We'll call them W's if you want. What does this have to be? M by N. M by N. We did that last day. That is really huge that we get that, because the only error obviously is to get them flip-flopped. So there is a matrix out there that will perform this, and that matrix is M by N. So if I now said I want to put zeros here, we just said let's suppose that N is bigger than M. N is bigger. That means I have more columns than rows. Absolutely, I'm going to have to parameterize in the end, aren't I? And I would have N minus M parameters. Oh, that means my null space isn't the zero vector, but it actually has dimension 1, 2, 3, 4, whatever. In fact, what's the dimension? It's at least the difference of N and M. That's at the very least. Could actually be larger than that. So is this mapping 1-to-1 in my scenario here? Is it 1-to-1? No, 1-to-1 meant that the only element in the kernel was the zero vector from this space. That's what 1-to-1 is. Bigger to smaller can't be 1-to-1. Can smaller to bigger? Can it? Yes. And how about same to same?
Yes.
Yes. Bigger to smaller is the only one that can't be. Okay? Again, going back to the span linear independence of vectors from the basis part, if I give you too many vectors, it can span, but it can't be linearly independent. Right? Because I'm, again, sort of like going bigger to smaller in the same sense. Now, as I do this or I do that, how much of W, which is the codomain, is actually going to be taken up? There's not a generic one-size-fits-all answer. It depends on the T I chose. We're taking things in R3, taking vectors in R3, and I'm moving them to a different vector in R3. So I'm going from R3 to R3. I'm taking things in R3, and I'm sending them to the XY plane in R2. Bigger to smaller. Okay? I'm taking things in R3, and I'm sending them all to the x-axis. Still bigger to smaller, but now I'm not using all of R2. I'm only using a line in R2. So even if I'm going from bigger to smaller, do I necessarily have to use up the whole second space? Again, I'm going from R3 to R2, but I want to make this overly simplified. Oh, I'm sorry, X1, R2. Okay, pretty boring. I'm taking points in R3, and all of them are going to be sent to, I'm sorry, vectors in R3, sorry. And every one is sent to a vector on the x-axis that has the same x-coordinate, but then 0 for the y-coordinate, and there's no z. That's not very exciting. Am I getting all of R2 back now? No, I'm getting a line. A one-dimensional subspace is what I'm getting back. I'm going from R3 to R2, but I'm not using up all of R2. I'm taking any vector in 3 space, x, y, z, x1, y, x2, y2, and I'm having it go to x1, comma, y1. I'm projecting it onto the xy plane in R2. Now am I using up all of R2? Yes. So in the case where I'm using up all of R2, that means my range, normally we sort of generically do the same thing with range that we did with kernel. We're saying this is a subset of this, which turns out to be a subspace. This is a subset of this, which turns out to be a subspace. in the case right here, my range is one-dimensional. But if in the case where I'm projecting it onto the XY plane in R2, now I'm going to get back all of R2. In that case, the range is all of W. What do we say if the range of T is W? What's the term we used? Then the mapping is, was one of the vocab words last week. Two syllables. First one's on.
Onto.
Onto, good, good, all right. One-to-one and onto are completely separate creatures. One-to-one only refers to what's happening in the domain. Onto only refers to what's happening in the codomain. Can a mapping be both?
Yes.
Then what criteria absolutely has to be true to be both?
And
Yeah,
must equal.
Good. They have to be the same dimensions. So whether it's polynomials, whether it's matrices, whether it's vectors, they have to be the same dimension. Bigger to smaller cannot be one-to-one. Smaller to bigger can't be onto. I can't take points on the XY plane and generate all the three dimensions. It's not going to work. Okay, I can only generate a two-dimensional subspace in 3. So that has something to do with rank, doesn't it? And this is a really huge one. Yeah.
The smaller to bigger can't, or the can't, it is one-to-one, right? That it can't be.
Can be. It's not automatic.
Oh, yeah.
Not a. It can be.
Yeah, it can.
If I give you too few tiles to cover the floor, very possible, highly likely they're linearly independent, but they still could be stacked, right?
Yeah.
But if I give you too few, they can't span. They can be linearly independent. If I give you too many, they can span. They might not, but they can't be linearly independent. So same thing here. Bigger to smaller, very likely is onto, can't be one-to-one. Smaller to bigger can't be onto, but it's very likely to be one-to-one. But again, I just gave you an example where I went from 3 space to a line. Oh, so therefore it wasn't going to be onto. So keep in mind, it all depends on the mapping that we're using. But the only way I can be both is if it's same to same, which is in the future what we're going to spend most of our time on, because that's where the really important stuff takes place. What I've been doing right now is mismatched, so it's easier to follow where things are going and where they come from, especially when we're talking about the matrix. Now, that matrix A, the matrix of my transformation, there's no system of equations. I'm going from one vector space to another vector space, and we're going to do it via a matrix. Can I talk about a row space and a null space? Can I talk about a row space of A transpose and a null space of A transpose with that matrix? Yes, that's what you just did. There's no solve the system of equations using a matrix. We are really beyond that now. That was a vehicle to learn things about matrices, but we're actually quite far past that. So let's do a simple example of something. I want T to go from, let's say, R2 to R2. I want the algebra to not be intense. Keep it simple, okay? And T of x1, x2, I could say xy, is, let's say, x1 minus 2x2 comma 3x1, how about minus 5x2?
This was an X1. First one, okay?
Thank you, x1. Does that look okay? You can all read that. I'm keeping it simple. So when I do this, I'm taking any vector in R2, and I'm getting it back a different vector. Is this going to be one-to-one? Is this going to be onto? I don't know. So if I wanted, let's always start with one-to-one. It's kind of like when you did linear independence. Why? Because one-to-one involves only the zero vector. Onto involves everything other than the zero vector, kind of like span. So I want to determine, when I do x1 minus 2x2 equals 0, and at the same time 3x1 minus 5x2 equals 0, I know this has at least the trivial solution as a solution. We know that. Absolutely guaranteed that a homogeneous system always has the trivial solution. Then our question is, are there non-trivial solutions? In general, you can't tell just by looking at it, so we do a little bit of work. So let's say we want to do this as a matrix problem. 1, -2, 3, -5, 0, 0. So, -3 of these plus this, -3 of these plus this, boom. And now let's do 2 of these plus this. Looks like x1 equals x2 equals 0 is the only solution. Great. What can I now say about t?
That is
T is 1 to 1. Why? WH1. Because the only solution to the homogeneous system was the trivial solution. Meaning the only vector that got mapped to 0, 0 was the vector 0, 0. Only the 0 vector here got mapped. Okay? If these had been multiples of each other, then I would have had to parameterize. Do you agree? And then that would have meant there are non-trivial solutions. I'm using R2 to R2 because we can't really mess up the algebra. Now, after all of this, can you give me the matrix of the transformation? If I'm calling this vector V, and I'm calling this result W, can you do this for me? Can you give me a matrix that would have pulled this off? What matrix could have pulled this off? I'm thinking of one. How about that one? Stare at that for a moment. Is that correct? If I take this matrix and I multiply it by this vector, I'm going to get this, which, so the matrix of the transformation, could I have just read this from that result? Yeah, you always can. In the textbook, that doesn't actually show up until the next section, but I'd like you to know that now because let's not waste any time. Oh, okay. Now, I would like the null space of this matrix. What's the null space of this matrix?
0.
Only the 0 vector. So we called this matrix A. So the null space of A is only the 0 vector. Now remember, the 0 vector is dimensionless. It's a point. Doesn't matter what dimension my space is, it's still the origin. It's a point that has no length. It has nothing. The null space of A is this. Therefore, the kernel of T is this also. We want to make sure we understand that. That's the kernel of T.
Is the kernel always the same as the null space?
The kernel of the transformation is the same as the null space of the matrix, but it's a different question. When I'm talking about the matrix of the transformation, I have rows and columns and all this stuff going on. And so answering the null space and all that stuff is like what we did before. When I'm talking about linear transformation, I asked this question without ever a matrix. We came up with the matrix. So the kernel is actually the set of things here that get sent to the 0 vector there, which is going to be the null space of that matrix. That's how we're usually going to find it. But depending on the way the question is asked, it's still going to be the same answer. Now, if I said, what is the row space of A? Man, that's easy there. You just look at that. That's why you always find null space first. But it's not the row space of A that I'm interested in this time. It's actually the column space or the row space of A transpose. And why is that? Because that's how my output is generally going to look. My output is actually going to look like, or I should say the dimension. The range of T, the things I'm going to get when all is said and done. Okay? The things that I'm going to get when all is said and done. If I'm going same to same, then my coefficient matrix is square. We like that because there's other things. You know, I can talk about inverses and determinants and stuff. But the problem is if I'm going from same to same, it's sometimes difficult to distinguish A and A transpose as results because they're all in the same dimension. Everybody got that? The question I asked you was non-square. It actually makes it much easier for you to separate things and categorize. What must be true no matter what is that the dimension of the row space of A and the dimension of the row space of A transpose, which is also column space, have to be the same. And those are defined as, what word? The dimension of the row and column space is called the what? Starts with an R. The rank. People confuse rank and range. The dimension of the range of the transformation. This is a vector space. The dimension of this vector space is the rank of the matrix of the transformation. And in fact, the range as a vector space is the column space of the matrix of the transformation. And if you're saying, well, I don't see that clearly here, this is why I like using mismatched things. So now let's do a mismatch, okay? Very specifically, again, I want to keep this simple. Let's go from R3 to R2. I don't need this to be huge for you to understand the concept. We're going to go from R3 to R2, and we'll keep everything nice. And I'm going to take okay. This guy lives in R2. This guy lives in R3. This is my transformation right here. I'm telling you what I'm doing to every vector in 3 space. I'm sending it to a vector in 2 space. I'm not sending it to the XY plane. So the first question we might ask ourselves is, am I going to get all of R2 back again? My answer is, I don't know. Not yet. Can you tell me the matrix of the transformation? I want A so that AV equals W. Can you tell me A without having to do the system of equations that we did over here?
One negative 2, 1.
2 negative 4.
Yeah, it actually is that easy. We like that, by the way. I'm going to formally show you this next day because the formal proof of this actually involves totally different things than we're looking at now. It involves what is it going to do to the standard basis and blah, 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 blah. It's a whole bunch of other stuff. But right now, as a practical sense, that's all I got to do. Okay? I would like to know what is the kernel of the domain. I'm sorry, the kernel of T, sorry, that lives in the domain. And I want to know what is the range of T that lives in the codomain. That matrix is the key. I don't have to solve systems of equations. So let's start by finding the null space of A, which will be the kernel of T. Remember, the problem started, there was no matrix. So asking you the kernel of T, that question is valid, but I can't find it by itself. I'm going to find it by using this matrix. So we want to solve AX equals the 0 vector. Now, I don't like this type of notation. I really don't. Why don't I like this? Can anybody tell me? I don't mind the A and I don't mind the X. Where does that 0 vector live? Don't I have 2 different dimensions going on here? Yes. Do you see a problem with that?
It doesn't tell you what dimension.
Yeah, what would you rather write here?
0 vector of the dimension.
But what 0 vector am I getting? One in
R2.
R2 or R3?
R2.
Now, would this be okay? The oxygen vector, I think it's called, right? I just made that up. That's actually pretty good. That's okay, because it says the same thing. But if you're not doing this, there's a possibility you are looking at the wrong dimension, and that can easily happen. I like using mismatch because it's easier to track and follow things, but at the same time, we can make errors that we can't make if it's same to same. So I'm solving this problem here, and the way I'm going to do it is just simply augment. Now, you could do this just using simple elimination, But on a bigger problem, of course you would use a matrix. So let's remind ourselves. So I have negative 2 of these, negative 2 of these, negative 2 of these, so 2 of these.
Wait.
Did I screw that up? Oh, 2, thank you, I'm sorry. I did, what did I do? I did something crazy. Okay. Does that look okay? I think we're good.
Yeah.
Let's go 2 of these. I am going to have to parameterize. Okay, and what do you got? X1, X2, X3. So which one do you want your parameter to be? X3. And what is X2? Negative 2t? Then what's X1?
Negative 5t.
Negative 5t. So X is negative 5t, negative 2t, t. If I factor out the t, then it's every possible scalar multiple, including 0, times that vector. This is very important that we always do this step next, because I'm looking for a basis. Okay, I'm looking for a basis. What do I want to use as my basis? That guy right there. Now, I've actually seen it, somebody was showing me a really terrible YouTube video on linear algebra a couple years ago, and the author said, always find it by replacing t with a specific value. No. What's the problem with that right off the bat? Well, we replace it with 0. It actually says, is any real number? Yes, t can be any real number. But if I replace t with 0, and that's how I'm finding my basis, I have a problem then. No, you don't do that at all. This is my basis because every multiple of this is going to generate that space. Now, could I have used positive 5, positive 2, negative 1? Different parameterization? Yes, there's an infinite number of correct parameterizations. That was just the first and easiest. Every multiple of this vector would work. So what I'm going to do is say the null space of A, which is equal to the kernel of T, the null space of the matrix of the transformation is the same as the kernel of the transformation that lives in the domain, is the span of negative 5, negative 2, 1. Okay? The nullity of A, which is equal nicely to the nullity of T. We use the same word. Nullity of a matrix is defined to be the dimension of the null space. Nullity of the transformation, is the dimension of the kernel. In both cases, what's my answer? Anyone? Say it loudly.
1.
1. Why 1? Only one vector. Ah. And we're overthinking that. How many vectors live in a basis is the dimension of that particular vector space. So the nullity, which is a subspace, is a one-dimensional subspace of what? Careful. Of our 3. Because, I'm sorry, I said nullity, I'm sorry, the kernel is a one-dimensional subspace of R3 because the kernel lives in R3. Now we want to look at the range. If I said, what is the row space of A? What is the row space of A? Wouldn't we all do this? Why can't that be my answer to the range question?
R3.
Because they live in R3. Oh, this is why we have to look at the column space. I can't show you that if it's a square matrix, can I? But that's why a non-square matrix makes it much easier. I am inputting vectors in R3, I'm outputting vectors in R2. Well, where am I going to get vectors in R2? I'm not getting them from the row space, I'm going to get them from the column space. So now, I think I can erase this stuff over here. So now let's look at A transpose. Now let's do row operations on this guy. We are not interested at this point. We're not interested in the null space of A transpose. We're interested in the row space of A transpose. Okay? Null space would be an exercise, but we don't need that. So I have 1, 2, 2 of these, 2 of these, -1 of these, -1 of these, -2 of these, -2 of these. Can we say that the column space of A, which is the row space of A transpose, they are the same thing, is what? It's the span of 1, 0, 0, 1. So far, so good? And that is also the range of T. So let's pick off all the easy stuff. The dimension of the column space, which we also know is called the rank. The dimension of my column space is what? 2. So do we agree the rank is 2? And what did we say the dimension of the kernel is, or the nullity? We just said it over there. 1. The rank plus the nullity has to add up to the dimension of the domain, which was 3. What's the dimension of the codomain? 2. Which is also the rank, which is also the dimension of the range. The dimension of the range is the rank. And so we defined rank earlier because we were only looking at matrices. There was no linear transformation. So what part of the matrix told us the rank? The number of non-zero rows when you do row operations. Or if I do the transpose, the number of non-zero rows, same number every time. We said that's the rank. But actually, a more precise definition is the rank is the dimension of the range, which is the dimension of the column space of the matrix of the transformation, which is also the dimension of the row space of the matrix. It goes backwards. It all leads to the same thing. But it's the sum that is extremely important. Rank plus nullity must add up to the dimension. Now, if I'm going smaller to bigger, think about that for a moment. If I'm going from smaller to bigger, let's say I'm going from R2 to R3. Then my kernel is probably only going to consist of the 0 vector, right? Which means that if I'm going R2 to R3, my nullity would probably be 0. Now think of the matrix of the transformation. Think of my row space for a moment. My row space would have to have dimension 2 because my nullity was 0. Now let's go to the other guy. I'm going from R2 to R3. What's the dimension of my range? It's still that same number 2 because that was the dimension of the row space. That's why when you're going from smaller to bigger, you can never be the bigger. You can't. Because the matrix of the transformation, I'm going from smaller to bigger, the highest the rank could be would be the smaller number. It could actually be less. But the biggest the rank can be is the smaller of the two numbers. I have a 3 by 5 matrix. The maximum value rank could be with 3. That's why smaller to bigger cannot be onto. Because to be onto, the range is the entire codomain, which means the rank has to be equal to the dimension of the codomain. And if that's bigger than my first one, that's impossible. Is that pretty cool with that? These are hurting your brain, I know, to some degree. But these are actually very simple rules to keep track of. Okay? Using dimension in your arguments to make your conclusion is actually a very powerful tool. We're going to spend most of our time in the future being everything after this week, going same to same. And same to same, we will do 2 by 2s, we will do 3 by 3s. We'll start with 2 by 2s because I want you to understand things conceptually, but I need the algebra to be trivial at first. Then we can move on to 3 by 3 where the algebra is more intense, but you have the concept down, so therefore all you're now worrying about is the algebra. I can't have you be learning the conceptual and the algebra at the same time. It's too much.
Previously you said the kernel of T was a one-dimensional subspace of R.
Well, no, in this example,
Yeah.
in this example, because my kernel consisted of the span of one vector. So that meant for that example there where we went from R3 to R2, I believe, our kernel was a one-dimensional subspace.
Of R3 or R2?
They live in R3, right? Yeah, so it's a one-dimensional subspace of R3. So that means my nullity was 1, but the dimension of my domain was 3. That means the rank had to be the rest, had to be 2. Which, by the way, was evident when I just simply looked at this. Oh, row space is 2-dimensional. But in this concept, I'm not really interested in the row space. In this one, I am actually interested in the column space. And by doing a mismatched thing, it was easier for you to see, okay, I had to look at columns to get that other number. But what if this was square? Now here's a dangerous thing, the row space and the column space, or the row space of A and the row space of A transpose. They don't have anything to do with each other other than their dimensions. The numbers are not going to be the same. So let's say we had a square matrix, and let's say we got 2 non-zero rows when we did all our row operations, so our rank was 2. Now I'm going to look at the transpose of that and do the same things. I should only get 2 vectors, but they're going to be completely different from the other guys. There's no relation, and they're not going to give you a dot product of 0. It's not like that. They're just 2 different 2-dimensional subspaces. And there's a couple of things I see people do. They think they're being clever when they're doing. They say, well, if I want to find the basis of the column space, I'll just take the first 2 vectors, and that will actually work really often. I can come up with examples for the rest of your life. Well, it won't work ever. You have to do the row operations on the transpose. And a lot of folks think they're being clever by taking these guys. What if I made my first 2 columns multiples? You would get the wrong answer on every question that exists, and you actually have seen that already. You've seen matrices where the columns are multiple. First 2, not the last 2. I can easily make the first 2 columns multiples. Really, what if I made that a -4? You can't take the columns of a matrix and make a conclusion. You got to take the rows of the transpose and do row operations. You have to. You can't do it any other way. And it's not a shortcut. It's a recipe for disaster. And some of you don't have any idea what I'm talking about. I have a row space of A and a row space of A transpose. I find them by doing row operations and looking at the non-zero rows left over. You can't simply take the dimension of the row space and just arbitrarily grab that many columns from the original matrix. Those columns are not necessarily linearly independent. In fact, if your original one had a rank that was less than the dimension, then your columns have to be linear combinations because your rows were. That's why you can't just take columns without doing it in row operations. Your columns are already linear combinations. So the columns you grab might already be combinations of each other, which means it's the wrong answer. Can't do that. Yeah.
What's the point of the column space in this case?
Well, the column space is the range.
But if I'm looking for the rank, I can just use the...
Right, the rank is a dimension.
Oh, right.
It's a dimension. So if all I'm interested in is rank, that's easy. I don't actually have to do anything. Once I find the kernel or the null space of A, I already know the rank. Everyone understands that now, right? Mm-hmm. I'm going to ask you out loud. I'm going from R4 to R5, and the nullity of the transformation is 2. I'm going from R4 to R5. The nullity of the transformation is 2. What is the dimension of the range? 3. Going from R4 to R5, and the nullity is 2. R4 to R5, and the nullity is 2. What is the rank? R4 to R5. Rank plus nullity adds up to the dimension of what? The domain. Period. Not the codomain, the domain. So if I said I'm going from 4 to 5, and the nullity is 2, then the rank is also 2, because 2 plus 2 is 4. So therefore, what's the dimension of the range? 2. It had nothing to do with the 5. If I went from R4 to R3, and the nullity is 2, What's the dimension of the range? Still 2, because the rank was 2. Does that make sense? Had nothing to do with the dimension of the second space. Now, the dimension of the second space has everything to do with whether I am onto or not. I'm going from R4 to R2. And the nullity, once again, is 2. Can you tell me the dimension of the range? 2. Therefore, that mapping is onto, because I was going to R2. It's actually that simple to make that kind of conclusion. Did I have to do any algebra? Well, no, I had to do algebra to find the nullity. I didn't have to do anything to find any of the other numbers because they're automatic. Everybody cool with that? They're automatic. So you're always going to start by finding the kernel of the transformation, which is the same as the null space of the matrix. That's what you're actually going to do, right? You're going to roll up your sleeves and find the null space. You now know the nullity because it's the number of vectors in that basis. And that nullity can, in fact, be 0. We love it when the nullity is 0 because that means my mapping is 1-to-1. I like 1-to-1 because when I'm going same to same and it's 1-to-1, then what else must it be?
Onto.
Onto. And you say, why is that? I'm going from Rn to Rn. My kernel is 0. That means my rank is n. So the dimension of my range is n, but I was going to Rn. That means it's got to be onto because the range is the entire vector space. Isn't that cool? It's actually that clean. Onto is when the range is the codomain. When I'm doing my mapping, I'm always mapping into something, but is something the whole second vector space? Well, if I'm going bigger to smaller, it's highly likely that my range is my whole vector space. But if I'm going smaller to bigger, then the biggest the range can be is the same dimension of the first space. I'm going from R3 to R5, the biggest the range could be would be 3-dimensional, which means it's not onto. I'm going from 5 to 3, very likely the range is all of R3. Does that make sense to everybody? I know this is like mind-numbing, but the mathematics, the algebra, I think we can handle, right? So rank plus nullity equals the dimension of the domain, period. Nothing to do with the codomain. But once I have nullity, then I automatically know the rank, which would think of the rank as the dimension of the row space of your matrix of the transformation. That's the gimme, because remember, when you're doing the null space, then you cover up that column of zeros and now you have your row space. The dimension of my row space is the rank, but the beauty is it's also the dimension of the range. Because the range is the column space, which has to have the same dimension as the row space. So when you're finding the nullity at this end, you can actually conclude whether it's onto or not at the other end automatically just using dimension. So now let's get back to the situation where it's squared, where my matrix of the transformation is squared. And you guys told me correctly that it's either both 1-to-1 and onto, or it's neither. If the only thing in the kernel is the 0 vector, that means the rank would be the same dimension as the dimension of the domain, which is also the dimension of the codomain. Onto. Life is good. When it's not 1-to-1, then it's also not onto. We are far more interested in the mappings that are both. They tell us a lot of information. So going forward, that's what we're going to spend time on, is the ones that are both, because now I can answer questions. So the next 2 classes are very algebraic, and it's not going to be a lot of fun stuff. Change of basis was bad enough in 4.7. It's way worse the next ones. But once we get that, then we're going to understand, because we're still writing things, vectors in terms of some basis, but now there's a matrix involved other than just the transition matrix. There's some crazy stuff. So next week is going to be one of the most intense weeks in terms of the algebra, not the concept, the algebra. But we're going to come up with some incredibly cool theorems that produce really powerful formulas, and then we'll be done with all the prep. So think of this as all prelinear algebra. The end of next week we'll be done with prelinear algebra. And then we actually start the meat and potatoes, the whole reason the course exists, the whole reason why you were taking this, the whole reason if you're an engineer or a mathematician or a computer science, that's why this is such an important course. And from the engineering world, yes, this stuff is used in physics, but I will give you some cautions. There are some mistakes that are universally made that are almost unavoidable because of the problem of using decimal approximations for things. The one thing you cannot do in anything matrix algebra is ever approximate any number. It changes everything. In other words, it will change whether a matrix is singular or not singular. I can't get a determinant of 0 if I'm approximating any number that nothing's going to cancel. It might be close. Remember, it's 0 or it's not. So there's a whole lot of problems we run into. We are going to work with only happy, friendly numbers so we can understand things conceptually. But then I will explain what happens when the numbers aren't happy and friendly. Okay, we're going to review in a moment. I'm going to ask you, do you want me to keep recording or not? I usually don't record the review. Okay, just once you go, stop it.